opposed to evolution is that we're thinking about things that are relatively short-term changes, relative compared to the evolution of gene frequency changes and the diversity of form and structure. So we're talking about how big are populations, where are they in space, what are the combinations of species that live in a particular place. Those are the things that fall under the realm of ecology. And this kind of cheesy graphic here is the envisioning of what ecology is. So we've really been dealing with these small two circles, individuals and populations, and how they change across generations. Individuals and populations also exist in space and grow and shrink. Right? And together they comprise these things we'll call communities that we'll get to in a few days, and then ecosystems and biomes and biospheres. And we don't have time to go very far. In fact, most of the biology department doesn't really get up to this ecosystem level. This is stuff that's done more in environmental sciences. When you think of something like global climate change, you're really talking about biosphere. What happens on the scale of a planet that's influenced by actions within each of these communities or even single populations that change that whole picture and how does it cascade back. So, like I said, we're not going to get up to these outer levels. We're probably going to get about as far as community. But we're going to emphasize these things that are changes in number, changes in distribution. And I started by saying I think there's kind of an artificial distinction. So we have ecologists and we have evolutionary biologists, but these are the things that drive evolution. And there are feedbacks when things evolve. Like you probably can put this together, and we'll explore it with hosts and parasites. When one of those species interacting with the community evolves, it changes the growth dynamics of all the others. Right? So it's not a real distinction, but it's a sort of perspective shift. Okay, so let me back up to the outline. We're going to start today with some building block things, and there's some math, so don't get freaked out. It's not hard math, but we're going to dig into life tables and survivorship curves and pyramids. Some of this stuff should look pretty familiar in order to build the blocks that we'll then look at when we start talking about density dependence and independence. So today is kind of establishing the groundwork. So one of the big questions in ecology is how big are populations? How fast do they grow? How do we know what they're going to be like in 10, 100, 1,000 years? Are they going extinct? Are they expanding rapidly? All of that's critical for us to be able to ask the last piece, which is what mediates growth and limits. So if we're going to figure out what makes it grow or shrink, we have to be able to put numbers on it. So let's start with a species we care about, us. This is the plot of the human global population over a long period of time. So it's about 12,000 years. So we can estimate going back to about 10,000 BC. Okay. Our current population is actually a little bit higher than this. It's about 7.6 billion on the planet. At about 10,000 BC, there might have been maybe 1 million people. It's hard to say. But what the plot shows you is this really dramatic uptick. Right? So for a long, long period of time, there were about the same number of people on the planet. There were some significant events that created increases in population size. They were so insignificant at the current scale that they don't really show up here. Things like the agricultural revolution, when humans figured out how to make some of their own food instead of just collecting it. Advances in things like the Iron Age, when humans figured out how to make tools that lasted longer and could do more things. And these changed the population, probably because they influenced the ability to extract resource and the predictability of resource. But it really didn't affect growth all that much. You have a couple blips around 0 AD, you get an increase in population. There are traceable effects that impacted the human population. One of the most dramatic is the bubonic plague. Look at the dip, how many people died during that period. So you can see that signature if you zoom in close on these graphs. But what's really impressive is that really in like the last 150 years, we've gone from roughly less than half a billion humans on the planet, to now about 7.5 billion. We're in what's called the exponential growth phase. So that observation led this guy, Paul Ehrlich, to write. So coincidentally, Paul Ehrlich was one of the guys who wrote that escape radiate coevolution theory. He got famous for this book called The Population Bomb. It was published in the late 1960s. And it was one of these doomsday books where he looked at this graph and he said, we're in a lot of trouble. Right? The population's growing at a rate where we're going to starve out populations, we're going to run out of space, the accumulation of waste is going to lead to all sorts of social and environmental and biological disasters. We'll get the explosion of whatever the next bubonic plague is going to be. Right? And to some extent he was right, to some extent he was wrong. Part of the reason he was wrong is that humans have the ability, which is pretty unique among organisms, to look into the future and create changes in behavior. And one of the really interesting ones is this movement in the early 1970s that you might recognize. You probably all know about the China one-child policy. Heard about that? Yeah, nod your heads like dogs in the back of the window. No? We'll get to it if you don't. So people think that this is sort of a draconian, crazy idea that the government enforces a one-child policy. And China wasn't unique. They just took it to an extreme. We had these things like in Indonesia and Singapore, there were propaganda movements that were funded by the government. In the US, there was an NGO called the Association for Voluntary Sterilization. This movement to stop reproduction at 2, no more than 2. Why 2? You get a mommy and a daddy, and they make babies. And how do you replace mommy and daddy? You make 2. If you make more than 2, your population grows. And it actually had a pretty dramatic effect. And you can see it if you look at, if you plot the birth rate. So we'll come back to this. But just to convince you that these things didn't just happen in a few parts of the world. This is life table science, right? It would be an incredibly boring lecture to walk through life tables and to do some of this math. So this is one of the rare parts of the class where I'm going to tell you, read the textbook chapter carefully. Work through some of the math to convince yourself you understand it. And I'll give you the basics of it. So life tables are important for ecologists. Like a lot of ecology and evolution, we pull from other areas of thinking. So this is, if you have an interest in insurance, if you always wanted to be an actuarial calculator, this is your life. Right? You make life tables. So this is a life table of human females in 2005 in the United States. A life table has a couple of basic elements. There's some variation, but you've got a table of age. Could be years, could be months. If it's a short-lived thing, it could be days. You have survivorship, which is the proportion of individuals that are left alive at a given age. So this is the proportion left from what's started. So it always declines, right? The LX, these are often called LXFX or LXMX tables. The LX always declines, right, until it eventually gets to almost 0. So there are a couple wild things that you just pick up when you look at these tables. If a human female in the United States makes it to 100, right, she's still got a 2% chance of making it. Or her life expectancy is about 2 years longer. Okay? That's pretty wild. Survivorship is not the same as survival rate. They sound the same, they're not the same. Survivorship is what percentage is left, or what proportion is left at an age. survival rate is the probability that if you made it to 31, you're going to make it to 32. So the human male survival rate has a real dip at about 21. And it goes back up a little bit, about 30. So you can think about why that might be. But it's not the same thing, right? So survival rate is a different entry, and it's not in this table. Fecundity is how many babies you make at a given age. That's the FX. In some tables, it's called MX, the birth rate. So we could go onto this table. We could look at 30-year-old females in the United States. Almost all females that are born are still alive at the age 30. So this is about 98%, if I'm on the right line. Their projected reproduction, the FX, is about a half a baby. On the right, 0.98. About 5.8 babies. Right? So the average 30-year-old class of female makes about a half a baby. Obviously, no mom makes half a baby. It's an average. So when you put those two things together, you get this thing called age-specific fecundity. This will come up again in a bit. The LX times the MX, or in this case, LX times FX, is the average number of kids in that class. All that sounds like not that interesting. It's interesting when you put it together into these projections. But work these parts and figure, familiarize yourself with the table, see if you can make sense out of that. When you take the LX-MX or LX-FX tables, I learned them as MX, the book uses FX, so that's not confusion. You can make some generalizations. So there are three basic categories of life histories in living organisms. We call them type 1, type 2, type 3 curves. They are characterized by familiar organisms. Type 1 are things that have a relatively high survival or low mortality when they're young, like humans in most places. And they live with high probability to some age and then have a high probability of death. Right? So these are things like grizzly bears and big organisms that have high investment. Type 2, that's the straight line, the blue. Those are things that die at a constant rate. So they're born, they have some probability of mortality. That's the same mortality at age 1 as it is at age 5, at age 10. It's relatively uncommon, actually. And the examples are typically things like birds, small mammals, like rodents, lizards. And then type 3 are these things that look like this green curve where lots of babies are produced. They don't have a very high probability of survival. Most of them die before they ever get to the adult stage. But if they make it to an adult stage, they live a long time. Trees are the cartoon version of this. They make millions of seeds, or at least tens of thousands of seeds, and they send them out into the world, and a lot of them germinate, and lawnmowers run over them, and rodents pull them up, and they don't have a high survival. But if they make it to the tree stage, not much takes them out. So these are the cartoons from your book. I don't know why the book picked a bighorn sheep. How many of you have ever seen a bighorn sheep? Any? Really, has nobody ever seen a bighorn sheep? Okay, 1, 2, really? That's pretty, it's not the most familiar thing. How about a panda? Yeah, okay, so pandas work. We should have a panda in the book. These, again, are things with high parental investment. Right? The propagule, the baby, has a lot of investment, has a high probability of survival. Parental care might increase that survival. We get these curves that look like this shape. Right? Keep in mind the axes, number of survivors and age. Right? Type 2, I just said this, so I won't belabor it. Things like lizards, birds, the birds at your bird feeder, they're the classic type 3. The type 3, there are all kinds of type 3. Annual plants, most weeds, mosquitoes, lots of invertebrates in the ocean. They just make lots and lots of babies. But you get, again, this really high mortality early, low mortality late. Once an oyster makes it into an oyster bed, they're there for the year until somebody pulls it out and uses it. So, like clickers. Do those curves make sense to you? Can you read a question? I can tell by the sound that the proportion of people suffering pollen allergies is way more than last week. I think when I said something about allergies, it like stimulated some psychosomatic response. All right, good. So you can read a graph, and you can remember 2 slides away what we said. This is good. It's encouraging. So obviously the answer is C, right? Ratio, juvenile mortality over adult mortality, not survival. So if you confuse the terms, it would be the other way around. The type 3 has high juvenile mortality, low adult mortality. You get a life value. Good. Basically keep you awake. Okay. What do you do with that survivorship curve? It tells you a fair amount, actually, about a population. So this is another way to look at populations. And they relate to survivorship curves. We're going to use humans because they're really nice examples. Again, you probably got this in like some high school class or intro. But just to remind you, these are called pyramids, population pyramids. They're not always pyramidal shaped. But they are literally a distribution of ages. In this one, we have blue that are the pre-reproductives, green are the reproductives, orange are the post-reproductives. These are 2 populations of humans with roughly the same size. So size meaning the total number of individuals. I think it's fairly arbitrary, except that in the book they're picking 2 groups with the same overall number and a different distribution. Right? So the emphasis here is that you might quickly think about, is the population getting bigger or smaller? You think about whether there are a lot of individuals. That has very little effect on the rate of increase. Right? What matters is the shape. And it's really pretty intuitive. If you're producing a population that's got lots of this base, what's going to happen to them in the future? They become the reproductives. The reproductives regenerate that base. Right? So when you get that flared out shape, you get the most growth in a population. When you get a shape like this one on the right, this is modern Japan, you got relatively few individuals in the beginning class. They become the reproductives, they don't replenish that base as quickly. Okay, so in the extreme, you can actually get the invert of a pyramid. And what's that going to tell you? That's a population on the way out. That's senescence. That's populations that are creating lots and lots of old individuals, but they're not replenishing the young class. So, the shape really, really influences that growth rate. And pyramids grow faster than bars or rectangles. It doesn't, a lot of these other pieces of it don't matter. And that's what this table is meant to emphasize. So compare Nigeria and Japan, 2 populations of roughly the same size, about 150 million and about 130 million. Right? Nigeria produces way more babies per female than humans in Japan. They've got a higher percentage of the population that are young. Right? That's the flare at the bottom of the pyramid. And yet Japan has lots of old individuals. They live a lot longer, almost twice as long. Right? Their infant mortality rate's way lower than in Nigeria. And yet, if you project this plot out for 40 more years, Japan's actually going to decrease in number. This is not a stable shape. The population size should shrink. How do we know that? That's the math from the life table. Right? Whereas Nigeria is going to more than double in 40 years if it persists with this shape. Right? So the point is, focus on that shape. The flare at the bottom is telling you who's going to be the next set of reproducers. And it overcomes what seem like really important things. You know, can we keep an individual alive a long time? Can we reduce infant mortality? Can we increase overall health and longevity? Those things don't matter at the population scale in terms of creating numbers. What matters really the most is birth rate and the distribution of young versus old individuals. This is just another graphic to show you how this looks. These are data from human populations. The way to read this graph is that pink was 1975, blue is 2000. So the difference between the pink and the blue are comparing the pyramid 25 years ago and what it looks like now. So the blue is the expansion. Right? And this data set's divided into the developed world, which has fewer individuals, and the developing world, which characteristically have high birth rates. You can see that the developed world, there's actually no growth in this major reproductive group. So that the fact that the shape in pink had a narrow base and a flare at the age of reproduction tells you that those reproductives are going to get old. We've got more blue up here in the old age classes, but they were never replaced. So there's no blue in that major reproductive age in the developed world because they weren't replaced by the previously young individuals down here. Compare it to this plot down here with the flare, it just expands, right? We even get more flaring out. So how would that change? You'd have to change something about the production of this early age class. So let's go back to the thing I started with, the one world policy. Here's what the plots look like for China. So if you don't know the one child policy, this was established in 1979. This was a response to the Maoist government really pushed make as many babies as you can because that creates a productive society. We get more resource, the population grows, everybody wins. So the result of that policy was nearly a doubling of the population size of China over about a 30-year period. Went from about 550 million to almost 1 billion people by 1979. That's pretty rapid. So there was one influential official who read some ecology and said, ooh, this could be a problem. And their response was, make one baby. So it's the only case I know of where a government actually enforced with penalties a fecundity rate. And it's not just one child. There were exceptions for rural communities, and it's not quite as simple as one baby per couple. But here's the pyramidal plot right at 1979. Lots of babies, a classic flared out pyramid. This is when that policy was instituted. You can see it become more of a rectangle, and then the estimation for another, 8 years from now is that we've got this basically no growth pyramid. How did they do it? They reduced the birth rate. They reduced the proportion of individuals who are in this bottom class getting reproduced. So on an actuarial sense, like ignoring all the politics and sociological impacts, that works. You reduce the birth rate, you reduce the shape of the pyramid, you make it narrow-sided, and you reduce the growth rate of the total population. All right, math. This is the only math go to the book, work it through. They work the steps really simply and clearly. This is about as simple as it gets. This is like y equals x1 times x2. So how do you get those pyramids? How do we know that in 2025 the pyramidal shape of the Chinese population is going to be more narrow and rectangular than it used to be? It's basically working out like this. So at any given time, you can figure out what small n is here. How many individuals are in a given age class? How many individuals are 30? How many individuals are 35? The total population is big N, right? That's the billions. And we can just take the number of individuals that have made it to a class, multiply it times the number of babies they should make in that age, and we would know how many are in each of the age classes and what the total population size is. So we start with a little table like this. This one has 3 ages. 0 is newborn. And the book will work through the math. I'll walk through one step so you can see where it goes. But you can figure out exactly how many babies there should be. So this looks horrible, which again is why I don't want to do it in a lecture. Right? But essentially what you're doing, let's just go to the age class 1, right? Here's the current number of individuals. 20 of them were born. That's the 0 class. Right? What's the probability that they make it to age 1? They survive. You have to multiply the survival rate of that 0 class, 0.3, so it's 20 times 0.3. That means next time around, how many 1-year-olds should we have? 6. 20 times 0.3. How many, and they go back into this total. So if we want to know how many individuals are in the population, we have to add all the survivors plus all the newborns. That's everybody. Right? So 1-year-olds make babies. Right? How many babies do 1-year-olds make? You go back to your life table, you go to age 1. On average, 1-year-olds make 2 babies. So how many babies are produced by 1-year-olds? 6 times 2, 12. Right? So that should give you, where are we? Yeah. 6 of the 1-year-olds has 2 offspring, they go into it, right? So that's 6 times 2, that's your 12. You do it for 2-year-olds, there are 24 2-year-olds predicted to survive. Each of them has how many babies? Go to the fecundity, 4 times 24, they go in. We also add all the individuals that survive, the 6 1-year-olds, 24 2-year-olds, and we would get an estimate for big N in t plus 1, and that would be 138, right? So that predicts growth of that population, 100 to 138, right? So I don't want to walk through all that. Go back to the book and work that through if it's confusing. Where are the probable trip-ups for you? Confusion over t plus 1 and t. These are just subscripts that tell you about time. Now is t, and t plus 1 is next year, or next generation. Right? So the t is just giving you a point, and t plus 1 is the next interval. Moving along these tables, you've got to go from an age class times the survival rate here to get the survivors next time, right? So 1 age class, 0, survives with a rate to become the next age class. So the 0s become 1s, the 1s become 2s. The current 2s make babies, and what age class do they go back into? 0s, right? The newborns. Every baby's into the 0s. So why did the 108 end up in this 0 line? Because 1-year-olds had babies, they go in here, 6 times 2. 2-year-olds have babies, 24 times 4, they end up in the 0 class next time. So work that through. I'm not gonna ever give you a question where you have to like recreate the entire table, but I might give you a question where I want to know what's the, well, for example, can you figure out from this little light table what the age-specific fecundity is of age class 1. So think back to what age-specific fecundity was. They talk to each other. At least it makes it less uncomfortable for me.
What's the fucking yeah, right? That's just like adding the number of newborns you have to how many people have survived. So like, don't think humans because that's confusing.
What?
I don't know.
T or T plus 1?
A 1-year-old hamster has a child. That child's going to be 0 years old when it's
I think
born,
it's
right?
T, no?
And even if you're a 2-year-old hamster, when that child's born, it's
That's
gonna
what
be
I thought, but that's like really
like a
straightforward.
child isn't born at age 2, like,
Yeah.
even though the 2-year-old
Yeah.
hamster had it. So every time they have children, it goes back to the 0 line because they were just born. And this is just adding, like, I think that this is the population. It's absolutely, but like, it's like all the hamsters having children at different rates than the next generation.
Okay, you're winding down. This is
Right. Well,
So
those
it takes you a lot longer if it has to do math. That's
for
my
each
first
different
observation.
age. Yeah, this is
The number of changes
It's just that not all the newborns
of
survive.
answer was
That's-
way more than usual. Like your confidence with math seems to be lower. So, what are the 2 most popular answers? One of them's right, one of them's not. The 2 most popular answers are B and C. Age-specific fecundity is the expected production of an age class. So fecundity
That's what we were just talking about.
of 2 for age class 1 is just the fecundity. The age-specific fecundity is the product of what do we expect for survivorship, what percentage made it to that age, times the fecundity. So the correct answer is C. So that means that our expected production of that class, based on the population size, is the proportion that made it to that age times their average reproduction. So on average, they're producing 1.2 weighted babies. Make sense? It's partly definitional. Yeah.
Can you explain again why you didn't use the survival rate?
Why what?
You didn't use the survival rate and use
Why would you use survival rate? So the age-specific fecundity is defined as this. If you want to know how to create that pyramid, you want to create a bar, which is the proportion that survive times the number of kids that are going to come out of that bar. The survival rate, you can turn into the survivorship by multiplying the rate times the number that were in that class. So they're not unrelated, but the survivorship is that proportion that made it there. So if you think about a long life table, you get down for humans down to 80 or 90, the survivorship's really low. Okay, so even if you had reproduction at that last age, they would have relatively little contribution to the next generation. So think of this as the thing that's going to create contribution from that age class. So you have to know how many are there, not whether they're going to make it. So the rate is whether they make it or not. Survivorship is how many make it or what proportion make it. Okay. Okay. Now, okay. Behave. Good boy. Okay. There. All right. Sorry about that. So, if we take those light tables, we can make some projections about what populations are going to do. So this is where the math comes in. It's scary because there is a Greek letter. You guys probably know Greek letters, right? What's this? Lambda? All right. So lambda is defined as this finite rate of increase. It's critical in population growth equations. You can look at specific, age-specific growth, so that Lx times Fx would give you the growth of each class, right? And you can see that they vary, right? Maybe there are fluctuations that have to do with what age, how many are in a given age class, what their birth rate is. Each of these colored lines is a different age, except for the orange one, which is the total, the big N. Big N damps out the differences between the others. So the total is less effective than each of the other age classes. Okay. So if we plotted the rate of increase, we can turn this orange line into this black line. Why do we want to do that? What's the rate? What is the rate of increase, or what's the proportional increase in any time interval? It's what it is now compared to what it was last time. So it's t plus 1 compared to t, or t plus 2 compared to t plus 1. Right? So each of these intervals, this is time, it can be generations, is t plus 1 compared to t. Lambda is the slope of this thing for each of those intervals, right? So we can take this orange line, look at that rate, that ratio, and look at it through time. So why does it go jaggedy and then go flat? Because if you take each one of those steps in that orange line, you can see that there's a decrease from 1 to 2, it's a negative slope. Then there's a rapid increase from 2 to 3, another decrease, and it damps out until it's relatively flat. Does that make sense? So it's a rate. It's the rate of growth. You can plot the rate of growth from data by comparing what's the interval change. In a population that's not growing, what do we expect about lambda? It should either be flat or negative. Negative. Right? If it's growing, the rate should be what? Positive. Okay? So, right away, if you calculate this lambda, or if somebody tells you, oh, this population has a lambda of 1.3, which is roughly what this graph shows you, then we know that that population should grow. So if lambda is positive, it grows. If lambda is 1, it's not growing. So if lambda is 1, what does that mean? It means that the population size at t plus 1 is exactly the same as it was at t. It didn't change. It's not growing. If t plus 1 is smaller than t, then it's shrinking. That's a declining population. So it gives us an instant read on whether the population's in a phase of growth or extinction, or at least decline, or whether it's stable. Stable's hard. It has to be exactly 1. Okay? So all this leads us to this concept called exponential population growth. So remember the plot on the first slide, the tail of it looks like this. You know, our modern population, the population bomb, is this swoopy upslope. And I want you to hear two terms and then ignore the difference. It's kind of dangerous. The book spends a lot of time drawing a distinction between geometric and exponential growth. They're the same thing. Okay? The difference is geometric growth is calculated assuming that the reproduction happens in discrete episode intervals, a sequence. So maple trees that are producing pollen right now and seeds, they reproduce once a year and then nothing, and once a year. Things like mice and humans reproduce continuously. They basically don't have seasonality. We call that exponential growth. The math is slightly different but equivalent. And so I don't want you to obsess about the difference between geometric and exponential. They do the same thing. So that's the message of this slide. Don't focus on why they're different. Focus on why they're the same. So I'm going to show you why they're exponential. Just think about exponential. This is the formula. You look at it and it's like, oh my God, what's that? It's got a Greek letter and a subscript and another subscript. It's two things multiplied by each other. The growth rate times the population that you start with. And you get what it's going to be next time. Pretty simple, right? I have to give a symposium talk this weekend. I kept doing that. There we go. All right. So we can do that across one generation. That's pretty obvious, right? We figure out how many individuals we have next year by taking how many we have this year, multiplying it times the rate. What if we want to know how many individuals we're going to have in 100 years? We do that 100 times. It's pretty easy. How do you do it 100 times? You raise that rate to the t power. So now t is how many generations? And that's the exponential piece of this. We just do the rate over and over and over again. Each time we increase the number of individuals, we multiply it times the rate. We bring it together as an exponential function. Okay? So this is the discrete version. We can do this in continuous terms with a slightly different math. We take e to the rt. Right? Where did lambda go? Lambda's gone. That was our growth rate. Now we have a new term for the growth rate. And they are not equivalent, but they mean the same thing. So this math can become the same. And this is what the book calls geometric and exponential. What you really need to remember is that lambda and growth rate r are essentially the same. They tell you the same thing. How fast does the population grow? Okay? Does that make sense? So, you can draw an equivalence. R, the exponential growth rate, is the log of the finite rate of increase. Those terms aren't really going to help you. What you really need to remember is that R is this exponential growth rate. They're describing the same process. The values are slightly different. R, because it's an exponent here in the equation, the critical values are different. So when R is 0, what is that like? That's like when lambda is 1. What is lambda 1? When we get e to the 0. So you can plot these things. You can look at growth rate. This is a classic semi-log plot. That means it's the growth rate, the population size on the log. The y is a log scale. Time is linear, so it's semi-log because it's log on one and not on the other. When we have exponential growth, on a semi-log, that looks like a line. If this was linear by linear, it would look like that curve I showed you a minute ago, right? This is linear scalar axis, and scalar axis, that's exponential population growth. If we change this scale here to a log, it looks like a line. Why do you want to do that? Because the numbers get so huge, you can't plot very easily. But you can immediately recognize exponential growth because it's a linear curve on a semi-log plot. Good? All right. Reinforcing this, basically telling you the same thing. How do we know whether a population is going up or down? We can look at R or lambda. Which one do we look at? Doesn't really matter. It depends whether they're discrete or continuous growing, but they tell you the same thing. So you should be able to look at that curve and go, oh, okay, what's population size doing over time? Getting smaller. This is a case where you have lambda less than 1 or R less than 0, right? Because it's the exponent. 1's the critical value for lambda, 0 is the critical value for R. What's this population doing? Nothing. Staying stable. Right? What is that scenario? That scenario is lambda is equal to 1. When is lambda equal to 1? When R is 0. Okay? The third possibility is the population is expanding. That's when lambda is greater than 1 and R is greater than 0. So what you need to remember is that R's critical value is 0, lambda's critical value is 1. One last, just so. How do we know, if I tell you lambda is something, are you impressed or not? Look at humans. Our current lambda is 1.01. That's pretty close to 1. That's incredibly close to 1. That still projects that we're going to increase the population size from 7.5 billion to about 10.5, 11 billion over the next 4 years. And if you want to have a little fun, you can go to this, there's a website that is the live population clock. And it's updating by country, by global population. There's some interesting plots there that show you the relationship between growth rate and what human population is. Okay. Enjoy this time.